For polar coordinates, they start off giving us some bold print terms here that are important. They tell me that so far you have been representing graphs of equations as collections of points x, y on the rectangular coordinate system. All right, if you think about it, when you go to plot a point, typically let's say we're trying to plot the point 2, 1. We go over 2 and we go up 1. That makes a rectangle. That's why it's called the rectangular coordinate system, the Cartesian plane that we plot those XY points in. What we want to do here, it says in this section, you're going to study a second type of system called a polar coordinate system. And whereas the Cartesian plane, the rectangular coordinate system, is based on rectangles, a polar coordinate system is based on circles. So if you flip through that packet that I gave you, you'll notice that there are several sheets in there that are just nothing but some concentric circle graph paper. That's polar graph paper. And you're not going to find that at Walmart, but you definitely could go print some offline if you needed extra. You should have enough there in your packet, though, for what you'll need to do. Basically, you'll notice that instead of making rectangles, it's basically we could go through and we could make a circle with a radius of 1 and a circle with a radius of 2 and a circle with a radius of 3 and 4 and so on. So you could hand draw them, but for more extensive graphs, that polar paper will be helpful for you. All right, so rectangular coordinate system based on rectangles, polar coordinate system based on circles. So a couple of points there. They tell us that what we normally think of as the origin can also be referred to as the pole in a polar coordinate system. And we usually call this the positive x-axis or the initial side of an angle. It's the polar axis in our polar coordinates. We're still going to start here and we're going to go counterclockwise to create a positive angle, or we're going to go clockwise to create a negative angle. And we're also going to measure the length from the origin or the pole out to our point, and that length will be a radius, as of course it would be on any circle. So the way that we write a polar coordinate is we'll have the radius value and then a semicolon and then our angle value. Most textbooks will put a semicolon in between r and theta. Our textbook does not. I'll write it that way when we're doing notes and quizzes and that type of thing, just so that it's very clear to you. If it's 2, 0, I don't know if that's an xy or if that's an r theta. And so if there's a comma, I'll know it's xy. If there's a semicolon, then I'll know it's r theta. So look at example number 1. For example number 1, they ask us to plot the point 2 pi over 3. So what I want to do is I want to start with the pi over 3. I'm going to start over here. I'm going to go counterclockwise. I'm going to go up about pi over 3 or 60 degrees. And then I want to go out a length of 3. So if my radius is 3, then I'm going to start right here and I'm going to go out 1, 2, I'm sorry, this one is 2. All right, so our radius is 2, not 3. I'm sorry, I was looking at this guy down here. So if our radius is 2, we'll start here and we'll go out 1, 2. Now here's what we want to be careful of. Again, this is circles, not rectangles. We just get in the habit of coming over here to 2 and going straight up, and if you do that, you'll notice you're going to be like way out here at 4. So you want to be sure that even if you don't want to draw all of these concentric circles, you basically could say, okay, I need to know the segment of the circle that goes from this value 2 right here to this value 2 right here. So you could just fill in that piece of the circle, and that would let you know how far to go out, even if you didn't want to draw the whole circle or if you weren't using a sheet of graph paper. All right, look at another one. For the next one, they give me 3 negative pi over 6. So just as we did before, a negative angle is just going to go down. So I'll go down pi over 6, or 30 degrees, and then I'll go out a length of a radius of 3. So again, I could connect the 3 on each of these axes with a part of a circle so that I could see how far out to go. All right, the next one that they asked me to plot is 11 pi over 6. All right, so 11 pi over 6, if I start here and I go all the way around, 11 pi over 6 is actually just 1 pi over 6 shy of 12 pi over 6 or 2 pi, right? That's actually the exact same point that we already have graphed. 3 negative pi over 6 and 3 11 pi over 6 plot as the same point. And that goes back to that idea of coterminals. Remember we said that if you added or subtracted 360, or in radians, if you added or subtracted 2 pi, you would get something that started and stopped at the same place. So it's the same idea here. That's why we're getting the same point when we plot 3 negative pi over 6 as we do when we plot 3 11 pi over 6. The next one that they asked me to graph is negative 3 5 pi over 6. Okay, what am I supposed to do with a negative radius? I didn't even know a radius could be negative. I thought it always had to be positive. Well, think about other scenarios. Forget radii and polar coordinates and that type of thing. Think for just a second. If you're plotting a positive 2, you start at 0 and you go over 2 to the right. If you have a negative 2, you just go the opposite direction the same length, right? Think about it up and down. If you have a positive 2, you go up 2. If you have a negative 2, you just go the opposite direction but the exact same length. So I'm going to do the same thing with a negative radius. All right? If I had a positive 2 going this way, then a negative 2 would just go the exact opposite direction, the same length. If I had a positive 3 going this way, then a negative 3 would just go the opposite direction and out the same length. So when they ask me to plot negative 3 5 pi over 6, I need to start with what does positive 3 5 pi over 6 look like. Okay, so I'm going to go around and say, okay, if I start right here and I go around to 5 pi over 6, here's 5 pi over 6, and I could go out a length of positive 3. So negative 3 then would just go the opposite direction, the same length. So that is the same point that we got for 3 negative pi over 6, 3 11 pi over 6. That's the same thing for negative 3 5 pi over 6. So by playing around with the graph, we basically just discovered the formulas that they give me on the top of page 740. On the top of 740, they tell me if you have a polar coordinate, r theta, and you want to find other names for that point, here are some formulas for ways you could do that. You could add 2 pi to your theta value, or you could subtract 2 pi from your theta value, because that's the idea of coterminals. Look at what we had right here. If you add 2 pi to negative pi over 6, you get 11 pi over 6. If you subtract 2 pi from 11 pi over 6, you go back to negative pi over 6. It was the same point. So we can see that works. The other thing that they say is that you can change your radius to a negative and add 1 pi to your theta value. And so sure enough, this 3, when it got changed to a negative, 1 pi was added, not 2 pi, 1 pi was added to that negative pi over 6 to get our theta value. Okay? So we've worked it out by looking at the graph and kind of using some common sense over here. Let's work it out algebraically over here. If I have 3 negative pi over 6, I could add 2 pi according to the first formula. So if I take negative pi over 6 and I add 2 pi, I'm going to need a common denominator of 6. So I'm going to multiply top and bottom of this by 6. That would be 12 pi over 6 with the common denominator. So then I can combine and I'll have 11 pi over 6. I could have also subtracted 2 pi. So if I subtract 2 pi, it's going to be this exact same work, right? But instead of it being plus 12 pi over 6, it's going to be minus 12 pi over 6. So if I subtract 12 pi over 6, negative 1 and negative 12 would give me negative 13 pi over 6. And then for the last one, it says that I can change my radius to a negative and just add 1 pi. So if I change that positive 3 to a negative 3, then I want to take negative pi over 6 and just add 1 pi to it. So that would be add 6 pi over 6. So that would give me 5 pi over 6. So again, here are those same points that we were plotting over here and finding out that they were different names for the same point. This now gives me an algebraic way that I could create those different names for the same point. So we get to example number 2. And example number 2 says plot the point 3, negative 3 pi over 4 and find 3 additional polar representations of it. So you can kind of go your own way here. You can find the other names by the graph, if that made more sense to you, or you can find the other names by the algebraic formula, if that made more sense to you. The nice thing is, if I'm using the formulas, maybe I don't really like 3, negative 3 pi over 4. So if I'll go through and find the other names first, I might find a name that I like better that might be easier to graph. We had said that before, that anytime they give you something, when we were working back with our trigonometry, anytime you give them something that you don't like the name, you can always just change it by using our coterminals. All right, so I'm going to start with my formulas here. The first one says add 2 pi. So I'm going to take negative 3 pi over 4, and I'm going to add 2 pi. So need a common denominator of 4. So multiply top and bottom by 4. That would be 8 pi over 4. So negative 3 pi, positive 8 pi, going to give me 5 pi over 4. I definitely like that name better. If I had my choice of graphing the negative angle or the positive angle, I like that one better. So I could start here and go around 5 pi over 4 and go out a length of 3. Or I could have started here and gone down negative 3 pi over 4 and gone out a length of 3. Going to get the same thing either way. So it's nice to have options. All right, the second thing they told me was that I could subtract 2 pi. So let's go back to our original, which was negative 3 pi over 4, and let's subtract 2 pi this time. Same rewrite of 2 pi so that it's 8 pi over 4. So if I have negative 3 pi and negative 8 pi, I'm going to have negative 11 pi over 4. We also said that we could change the radius to a negative, and if we do, that we would add 1 pi. So let's try that. Let's change the radius of 3 to a negative 3, and let's take our angle that was negative 3 pi over 4 and add 1 pi. So if I add 1 pi, that's 4 pi over 4, then I'll just get pi over 4. And again, you can see if I came up here pi over 4, a positive 3 would go this way. So a negative 3 should go this way. Now, in your textbook, as part of example number 2, it says find 3 additional polar representations of this point using only values between negative 2 pi and positive 2 pi for theta. Now, if I ask you to give me multiple names for the same point, I don't care if it's between negative 2 pi and positive 2 pi. But they do that in a textbook, and they do that on the homework. So that's the only reason that I pointed out to you. On the homework, you would not see this answer given because it already was a negative 3 pi over 4. If you subtract 2 pi from that, that's definitely not going to be between 2 pi and negative 2 pi, right? So you would not see that answer listed. Okay, great. Well, then where are they going to get a third value? Once you create this new point right here, the negative radius with the new theta, you could find coterminals for that new theta, right? So you could add 2 pi or subtract 2 pi from that. This is already a positive. I don't want to add 2 pi or it's going to be too big again, right? But I could subtract 2 pi. So you get the idea that we could go on forever with this. I mean, you could keep adding an infinite number of 2 pi's and negative 2 pi's to either the original angle or to the angle that you got with the negative radius. So there are an infinite number of different names for this same point. We have lots of different things that we have 2 ways of doing. The thing that I think of most often is, let's say we wanted to measure the length of the classroom. You know, we could use a yardstick or we could use a meter stick. 2 different units of measure, the metric system or the English system of measure. I could use either one of them. What would be helpful is, you know, when you're first learning the metric system and you're not very familiar with it, it's really helpful when they give you some equivalents. They're like, you know, there are this many yards in a meter, or there are this many feet in a meter. So you just kind of get a concept. And that also gives you a way to have some conversion formulas to convert back and forth between those 2 things. So they do the same thing here with the polar coordinates. When we represent points, we always think of them as XY ordered pairs in the Cartesian plane, rectangular coordinates. So it would be nice if we had a way to convert back and forth between rectangular and polar, if we had conversion formulas for that. And so that's what they give us here. On the bottom of page 740, they tell us that we can do coordinate conversion. with x is equal to r cosine theta, y is equal to r sine theta, tangent is y over x, and x squared plus y squared is equal to r squared. Here's where they're getting that. We already know that cosine is x over r. If you multiply both sides of that by r, then you'll have x is equal to r cosine. So this is not a new formula for us. It's just a modification of one we already know. Same story, sine is y over r. Multiply both sides of that by r, and you've got the formula you're using for y. And then these are formulas that we had used previously this year as well. Okay? So let's start with, what if I have an r theta, and I want to convert it to xy. So I want to convert from polar to rectangular. Then I need to use the formulas for x and y, right? So let's start with x. They told me that x is equal to r cosine theta. So since r is 2 and theta is pi, we'll come down here, and in the place of r, we'll put 2, and in the place of theta, we'll put pi. Now, you may remember those values like cosine pi. If not, you're welcome to throw those into your calculator. So cosine at pi is -1. Be sure you're in radian mode if you're using your calculator. And so 2 times -1 going to give us -2. All right, now we need the y value. So the formula they gave me for y is equal to r sine theta. So let's put 2 in for r and pi in for theta. Sine at pi is 0. So 2 times 0 will give us 0. Now, we've said that these are two different ways to do the same thing. Two different ways to plot the same point. Let me show you what I'm talking about. Let's say that we wanted to plot the polar coordinate 2 pi. I would start at the polar axis, and I would go around to pi, and then I would go out a length of 2 on my radius, right? So I would get this point. If you plot the ordered pair -2, 0 in the xy plane, it's that exact same point. It's two different ways of doing the exact same thing. They're going to give me the exact same point. Just like if you measure something in metric and you measure something in English, you're still going to end up with the same length. All right, look at another one. This time they give me square root of 3 pi over 6 for my polar point, and we want to switch that to an xy. So again, using our formula, x is equal to r cosine theta. Cosine at pi over 6 is square root of 3 over 2. So square root of 3 times square root of 3 over 2 is going to give me 3/2, or 1.5. And if you're finding y, we're going to use r times sine theta. Again, r is square root of 3, and theta is pi over 6. So sine at pi over 6 is 1/2. Now, if you're doing this on your calculator is not going to give you square root of 3 over 2. It's going to give you 0.866. That's fine, even if you're in a multiple choice setting on a quiz where I've given you the exact value and you have a decimal on your screen. You can always throw square root of 3 over 2 into your calculator and see that it's 0.866. Alright, so now let's go the opposite way. You'll notice we're going to use the same 2 points that we already used. So I know what my answer is going to be before I begin. I've got 2 pi is equal to -2, 0. So I know -2, 0 is going to equal 2 pi. I've got square root of 3 pi over 6 is equal to 3/2 square root of 3 over 2. So 3/2 square root of 3 over 2 I know is going to be square root of 3 pi over 6. But how do I get that? All right. Well, let's start with, I need to know my r value. So I'm going to come up here and I'm going to use this formula, x squared plus y squared is equal to r squared. So x was -2, y was 0. So if I plug that in, I'm going to get 4 is equal to r squared. Take the square root of both sides, and I'll get plus or minus 2. You can use either the positive radius or the negative radius, but I am always going to use the positive radius, because of that formula that we learned earlier today, that when we use the negative radius, we have to add 1 pi to our theta value, right? So let's just keep it simple. Let's use the positive radius, and then we don't have to worry about adding things in or maybe accidentally forgetting to do that. All right, then I need to find theta. And again, I only know x and y, so I'm going to use this formula for finding theta when I know x and y. So I can say, okay, tangent is equal to y over x. Y was 0 and x was -2. So basically we're saying where is tangent equal to 0? And you could use the inverse tan button on your calculator there if you wanted to, that Jeopardy button. So second tan. When we did this without using our calculator, when we were using memorized values, we would say that tangent is sine over cosine. And if we're looking for where that's equal to 0, the only way a fraction ever equals 0 is that numerator is equal to 0. So we could say, okay, where's the numerator sine equal to 0? And that's at 0 and pi. Okay, great. I'm getting 2 answers. How do I know which one it's supposed to be? I can see it's not supposed to be both. It's supposed to be 2 pi. But when I get here, how will I know which one to use? Go back to your original given point. When I look at this original given x, y value, x is negative, y is positive. So if I think about that, that's over here at pi. That's not over here at 0. And so that's how I can see which one to use. Why am I getting 2 different values? Because remember we had the 2 different radii over here, and we had said that if you use the negative radius that you have to add pi. So if you think about it, -2 paired with the 0 would be the same thing as +2 paired with the pi. It's 2 different names for the same point. So that's why we end up with 2 possibilities there. So we have to be careful that we pair it up correctly with the radius that we want. We're going to choose the positive radius, and then the way to know which one of these to use is to look back at our original point and say, okay, where was -2, 0? -2, 0 is over here at pi. It's not over here at 0. And so that's how I'll know which theta to choose. Look at another one of those. Again, we want to find r. So we'll use x squared plus y squared is equal to r squared. So x was 3/2 and y was square root of 3 over 2. 3/2 squared is 9/4. Square root of 3 over 2 squared is 3/4. So we already have a common denominator. 12/4 will reduce to 3. Take the square root of both sides. Be sure you put in your plus or minus. But we said to keep it simple, we could choose the positive radius. All right. So now I need to find my theta value. So we can say tangent is y over x. Y was square root of 3 over 2. X was 3/2. So when you divide fractions, you multiply by the reciprocal. If I multiply by 2/3, the 2's will drop out, and that'll leave me with square root of 3 over 3. So again, if you want to, you can use the inverse tan button on your calculator. It's not going to give you pi over 6. It's going to give you the decimal equivalent of that. But again, you could match that up with no problem, even if I gave you the exact value. We know tangent's positive in the first and the third quadrant. So I get down here, and again, I'm like, great, which one of these am I supposed to use? Go back and look at your original point. In our original point, we had a positive x value and a positive y value. Is that first quadrant or third quadrant? First, right. If this had been negative and negative, then I would have needed to give the third quadrant value. But because they're both positive, I know I'm in the first quadrant, I'm going to give the first quadrant value.